Intro to AC lecture. In this lecture, we're going to talk about what is AC, how is AC made, and why we're using AC over DC, and some of the terms that we use when we are using AC. So let's start with the question, what? What is AC? Well, as everybody knows, AC is short for alternating current. DC was direct current, alternating current, as the name suggests. It alternates the direction. As it's alternating the direction, there is a change in voltage. All right, we'll see how that works. Now, why are we using AC? I mean, we have perfectly good DC. In fact, all of our electronics likes to use DC because it is constant. Unlike AC, it fluctuates, right? It is a constant source, and we want to have a constant source of power, right? We want to have a constant source of voltage and current. Why are we bothering with AC? Well, that's because, I'm going to give you an example. We have a fire triangle, right? The fire triangle suggests you have a fuel, and you have ignition and oxygen. If you have all of these three, you'll have a fire. If you remove one of these three, then you don't have a fire. Just like a fire triangle, well, AC, electricity, has a triangle itself. You have relative motion, magnetic field, and conductor. All right, typically this will have a form of a coil of wire, but if you have these three, you can create an electricity, which means you can create current, right? If you remove any from these triangle, from the three, then you're not going to have electricity, right? It is very easy to create. So how do we create DC? Just look at your battery. How does that create DC? Well, the DC is created by chemical reaction, right? Somebody has to put together different chemical mix, and through that process, the reaction of the chemicals will create the electricity, and that is DC. So compared to that, it is very easy to make, because the only thing you have to do is a motion between the conductor and a magnetic field. It is very easy to create. That is why if you go to the power plant, whether it's a wind turbine or water dams, right, nuclear plant or core burning plant, what they're essentially doing is they're turning the magnet within a coil housing with the power that is generated or sourced from either wind or water or fire, steam, so on and so forth. It is very easy to create. It also is very good for transporting as well over long distance. But we're going to talk about that when we get to the transformer, so I won't get into that right now. So there are two misters that we need to look at when it comes to AC. Michael Faraday and Heinrich Lenz. So let's see what they say about AC. Faraday's law indicate that changing magnetic field inside a coil of wire induces an EMF, aka electromotive force, aka voltage. All right, Lenz's law states that direction of the induced current opposes the change in magnetic flux that produced it. So what are they talking about? Well, the Faraday's law is suggesting, Faraday's law is suggesting that about the induced current and voltage magnitude. If you have a movement inside what I just explained in magnetic field and a conductor, then you're going to create an EMF, electromotive force or voltage. If you have voltage, definitely you're going to have current. All right. So that's what it means. If you amplify any of these three, then the magnitude of the induced current or the EMF will also be enlarged as well. All right, magnified as well. Lenz, however, talks about the direction of which way that current is going to flow, right? It says that it wants to pose the change of the magnetic flux that created it or produced it. So if the magnetic flux coming in this way, the current that's generated wants to push that back with the force, all right? If it wants to leave, then current wants to keep that from moving away and going the opposite direct by pulling it the opposite way. So Faraday suggests that it's a magnitude, and the Lenz talks about the direction of where that current is headed. Next, I'm going to help you visualize what that AC current looks like. When you think of an AC current, people often think of a sine wave. Why is that? Why can it not be a cosine or tangent for that matter? Why sine wave? Well, let's see. So what I have in front of you is I have the magnets, north and south, with magnetic flux lines, which means magnetic field, right? Visually represented. This indicates the rotation of my conductor. Okay, it's circling this way, and obviously on the right we have a graph to represent and visualize why AC is represented in sine graph. Okay, so this is a conductor, right? Instead of rotating the magnets, I am going to rotate the conductor wire, right? It doesn't matter. As long as you're rotating magnet or the conductor, then you are going to create an EMF or current. So I'm going to start like this, and we're only going to follow this black tape, all right? So this is where we're going to start, and it's going to be rotating like so, right? 0, 90, 180, and so on and so forth. Right now, I'm outside my black tape, this wire, right, is outside of the magnetic field, right? And I have no motion right now. It's not in the magnetic field. So am I creating any current or any EMF, the voltage? No, I'm not. Now I'm starting to rotate. This is about 45 degrees. I have started to cut across some of the magnetic field, right? So I have a relative motion by cutting across, and inside the magnetic field, I am now generating current and the voltage. I'm continuing my path all the way to 90 degrees. Look where my coil, right, my conductor is in relation to the magnetic field. I'm fully immersed. I'm right in the middle. This is where the strongest magnetic field is, right in the center. I'm fully immersed, which means I'm going to induce the maximum amount of current, maximum amount of voltage. And as I fade away at 135 degrees, 45 degrees later, right, I'm moving away from the center where the strongest magnetic field is. I'm going to the less and less and less voltage inducing and to a 180 degree from where I started. Again, I'm not in the magnetic field, therefore I'm not creating any current or EMF. I'm continuing to turn. Now I'm cutting the other way, right? I'm going down, right? I'm cutting the bottom side of it. So I'm going to generate more current. And until I hit 270, right now I'm back at where the magnetic field is the strongest. I'm fully immersed right in the middle of it, right? And I'm going to generate the maximum amount of voltage and current, but in the opposite direction. Before I created it right there, but now I'm creating an opposite direction. As I'm going back to 0 degrees where I started, I'm cutting less, I'm moving away from the center, and boom, right there. I'm back to 0. So let's look at that. This is how my travel was, right? My conductor. Let's grab another pen, right? Where I started here, I created no voltage, and around there, my 45 degree, I was somewhere around there, right? In 90 degree, I was here, and 180, I was outside, 270, and there you go, right? Right there, my 90 degree, there, 180, and 0 degree, of course, for that matter, and like so. You guys see that? Now let's translate to our graph, right? At 0 degree, we have no voltage. My coil is now part of the magnetic field. I'm not inside, so I got 0 voltage, right? This is voltage. This is voltage, right? And as I'm turning, I start to generate some current at 45 degrees, right? Let me just indicate. This is my 90, 180, and there you go, right? And at 90, right, I'm at the maximum point. At 45 degree, I'm right there, right? This is 90, let me write this down, okay? And this is 180, this is 270, and this is 360. Put this down. And again, oh, I didn't point this right there. And 45 degrees later, I'm down here, right? 180, I'm again outside of the magnetic field, which is right there. And going the other direction now, following the path right there. And 270 is where my max induced voltage was in current, and back to 0 at 0 degrees. So if I was to draw this line by joining the dots, there you have it. You have a sine graph, right? Not cosine. It didn't start from 90 degrees. It started from 0. We have a nice sine graph. So that's why the AC is represented as sine graph, because of this manner. Next, I want to talk about some of the terms that we use in an AC, especially when it comes to a sine graph, right? We have a cycle. And these terms, we need to know. It will help you understand going through this entire AC course. So you must be familiar with these terms by heart. You have to have them memorized, right, and understand it. What is a cycle? Well, cycle is one full revolution, right? One full travel, one full revolution travel, all right? Or rotation. Okay, that is cycle. Next, we have period. And period is symbol T. It's a time. What does that indicate? You guessed it. Time it takes to complete one cycle. How long does it take to complete one cycle? Okay, we figured out the cycle. We know what the rotation looks like, right? We know what the revolution looks like, but how long does it take? That's pretty important to know, right? Because of time, what do you think the unit's gonna be? Yes, it's in seconds, right? The symbol T, period is represented as T, and it's and is measured in seconds. The next, frequency. Right? Often when we talk about AC, frequency is big deal. Yes, it is big deal when it comes to AC. And we'll talk about it in the future lectures, but let's talk about what the frequency means. Right? Frequency, it has a symbol of Greek letter F, right? Or small f, it's fancy. And what is it? What is a frequency? Frequency is number of cycles per second. Okay? Between period and frequency, you have to have a clear understanding. Okay? All three of them complete each other, right? Because cycle, obviously, it begins with cycle. One cycle, right? This one, period, is talking about how long does it take to complete one cycle. I only care about one cycle. How long does it take? The frequency talks about, I don't care about one cycle, two cycle, but I'm just all about time. 1 second, how many cycles am I getting? How many cycles are completing within a second? So somewhat they are related, and this is measured in hertz. Okay, so how are they related? Well, think about it. If you have a cycle that's completing in 1 second, 1 second, 1 second, boom. It takes 1 second to complete one cycle. What is my frequency? Well, how many cycles per second? 1 cycle. Okay, cool. But what if I increase my period? Let's see what happens. If I increase my period, so now the time it takes to complete one cycle, it becomes 2 seconds. I increase the frequency. So I increase the period, the time. What happened to my frequency? How many cycles am I completing per second? 1? No, not even 1. It takes 2 seconds to complete one cycle, right? It's half. So it decreased. By increasing the period, I've now decreased the frequency. And that is exactly the relationship. It is inverse. So you will see that in formula, you will see the T period is inversely related to frequency, or frequency is inverse of period. So first thing that you have to figure out is cycle. That is a determining factor for finding period and frequency. Where is my cycle? Once you figure that out, you can then, depending on the situation, depending on how the graph is giving it to you, it may be giving you the frequency, it may be giving you a period, right? You're going to have to look at the graph, and then how long does it take to complete one cycle? If you know the period, you can definitely find the frequency. So let's look at some examples. How did you find the examples? Were they challenging? Pretty straightforward, but these are the ideas of figuring out the frequency or the period given the graph in front of you. Next, I want to talk about the voltage. We've looked at the x-axis in the graph, right? And let's look at the y-axis, right? Y-axis represent the voltage. Now, going back to the beginning of this lecture, the video, right? I said that alternating current, it has a fluctuating voltage and current, unlike DC current. So which means I'm going to have a different values at given time. So let's look at it. All right, here is my time, okay, and here is my voltage. And this is, as you've seen from my previous, right, explanation, it follows a sign, which means all of these have different values. All of these have different values at given time. And these values at any given time is called an instantaneous voltage. Instantaneous voltage, which means certain voltage reading at certain amount of time. Okay, that is an instantaneous voltage. Now, does this graph look like it has peaks? Yep, 2 locations, right there and, oops, right there. Forget about this line, right? I have a peak here, and I have a peak here. Gets in the negative side, but we still have peaks. So we have the peak values of the voltage. And another way that we can put it is, it's often represented as peak to peak value. And we write that like so, peak to peak value, which is if this peak value from 0 was 10 volts, my peak to peak value is going to be 20 volts. Make sense? Lovely. All right. Before I talk about the next value, I want to talk about this positive section of the graph. This positive section of the graph is called a positive alternation. Makes sense. Therefore, this part of the cycle is called a negative alternation. Alternation. Okay, in a cycle, we have one positive, one negative. Good? Lovely. Okay, let's talk about the last value. The last value is, don't you want to know what the average value for these fluctuating lines or the values? Well, that's exactly it. And that value is called a RMS voltage. And this voltage, RMS voltage, is the average voltage of all these lines, right? Remember, if this is on a negative side, but that doesn't mean it doesn't have power. It still has power. It still has voltage. It still has current. So if you're seeing a light, you're going to see from 0, you're going to see a light that was extinguished, go dim, bright, dim, off, dim, bright in the negative alternation, and goes dim again to off, right? So it is an average value, right? And it is also a DC equivalent value. Peak value is not going to be a DC equivalent value because it doesn't stay on like that. If you were to add all of these lines up and divide it by all of these points that you added, number of points that you added up, if you divide it like that, that's how you find the means, right? That's how you find the average. Well, the RMS, root means square, exactly came from that, okay? Exactly came from that. We're taking the means of all of these voltage points, all right? So how do we calculate that? Well, we're going to calculate exactly what I just explained to you. You're going to start adding all these. Let's go. Well, no, right? Well, no. That's, we found a smarter way to do it. Somebody was smart about it. Well, it's going to be around. What would you say the average value is going to be? Well, how about 45 degrees? Well, that seems right about average, right? Like in the middle, that's exactly it. So the formula for finding out the RMS value is peak times 1 over root 2. 1 over root 2 of sine graph is 45 degrees. Okay? So essentially this is 45 degrees. 45 degrees of voltage to peak, right? Let me give you an easier number, right? Let me do the math for you here. This is equal to voltage peak times 0.707, right? You can pick and choose which one you use. I like to be simple, so I've done the math for you. 0.707 is going to be the number that you want to use, right, to calculating the RMS value, right? So as long as you know the peak, you just have to times that by, multiply that by 0.707, then you'll have the average voltage for that sine wave, right, for the alternating current. It's pretty simple, right? So just like how we figured out our frequencies and period, let's do some examples on voltages.